Very good evening, guys. Can you hear me? Thank you, Arad, for confirming. How are you guys doing? Very good evening, Arad. Thank you, Ekta, for confirming. I remember, Ekta, you were not in the last class, right? What happened? Is it the related? Oh, you were there. Okay. Okay. I was not seeing responses, so that's why I was asking. That's good. So, okay. Are you like fine now? Or still some health issues or anything like that? Thank you, Sanvas, for asking. I'm doing good. Today, actually, yes, it was very good day in office as well. So I completed, I think, 4 to 5 tickets, and it was interesting work also related to NGNX and little bit close to the thing which I like most. So yeah, that was the work today, and so yeah, it was excited day. I do not wait. I do not need to wait for any permissions because in the PayPal or bigger organization, you sometimes have to like wait for some more permissions for the system wise or all those. So today it was not any hectic things. So it was very nice day, and at the end, like completed some of the PRs. So feeling good. Health wise better. Yes, yes. Health wise also I'm better now. So cold and everything is has gone. So yeah, I started running also because I think till Deepavali or after that I was just taking break. I was not going for running. So yeah, I started that as well. So yeah, it was good day, and I'm thinking this class will be excited today because I am planning to today discuss a lot of good questions today because I can jump into the BST as well, but I have seen that we have started understanding about the binary trees. So I want you guys to feel about it because see because this is binary trees are not at all difficult. You just need to take the feel of it. You need to understand how to recursively go to each node, or how to consider each of the subtrees, like each part of node as each part of a tree as a subtree, and then solve that subtree and then go back to the root node. So we'll talk about all these things today. Yeah. Is there raining, sir, in your place and all? No, actually, it's not raining. I think from I think 4 to 5 week. I think yeah, 4 week has happened. It's not raining, but yes, weather has changed. Not sure about the 4 week, or might be 2 or 3 weeks, but it's not raining in my area. But yes, weather is chill. Here in Chennai, all day raining. Ah, okay. I remember, I think Madhya Pradesh, like after center state, that the Madhya Pradesh, I think weather is normal, right, for every of the state, like in the Hyderabad or in Mumbai or in Pune, right? I'm not sure about the Calcutta side area, but I've seen that weather on these areas did not fluctuate. It just and each in a whole year, it just fluctuate between 22 to 35, something like that. But in my side, or like on the if you go above to Madhya Pradesh or go towards the UP, Delhi, Haryana, or little bit more above, or might be in the east side. So weather here it changes, it's fluctuate too much. I think temperature sometimes goes near to I think 12 degree or 13 degree as well, or might be lesser than that. Not sure about that. So might be because of that, it a lot of difference in the weather. So a lot of things changes with that as well. So yeah, that's all about the regional talk. But anyone has practiced the iteration, like I when we left our last class, so at that time when the last topic which we discussed, that was the DFS, where we are trying to traverse a binary trees. or trying to read all the notes in a tree. And while we were doing the DFS, I told you three ways under the DFS, which was pre-order, in-order, post-order. And I think the recursion way was very easy. We just need to change the orders, and code was automatically ready for us. But yes, in the iterative way, there are some bigger changes. So anyone tried to go for in order or post order? Because pre order we have already covered in the class. But what about the in order and post order? Anyone has tried to do it with iterative approach, or anyone has tried the BFS one? That one also left, right? Okay, so it looks like nobody has tried, or they are still figuring it out. Have I said this or not? BFS or video, okay, using queues. Yes, for BFS, definitely we are going to use the queues. Okay, guys, so that's what from the last class. So let's start our today's session. Yesterday also there is session, sir. Yes, I think on Friday we have session. Yeah. Okay, so let me share my screen and quickly revise it, guys. Whatever we did in the last class, we will do the revision. And I think if you guys have seen my comment on the LinkedIn about the absolute complete binary tree or complete binary tree, I have pointed it out in the last class. If you remember, Likit was pointing it out again and again about one thing that was about the left to right scenario. We'll talk about it when we will jump into the absolute complete mandatory. So we'll talk about it again. And like whatever was Likit was saying, that was totally correct. I read it again, the lines which was mentioned in the definition, and it was saying left to right, but I was always considering left scenario. So that's what we'll see about it. Yesterday we had a guest lecture. Ah, okay. So guest lecture. What was that about? Is it about the? I remember you guys have guest lecture about the. Oh, okay. Stack. Okay. How was that? Fine. Ah, great. I know. I'm sure like you guys have learned something new in the stack, and that will definitely help you in your interviews or while problem solving. Very nice. Very nice. He told the same problem you explained. Ah, okay. So might be like he has taken the same slide to explain the stack concepts. Ah, in one way it was revision. But I remember you guys have already done the revision, right? So you guys can ask Ansul to like go for new topics like TypeScript, GraphQL, or this type of some of the topics you can ask to the Ansul to talk about in in the guest lecture. Those will be very interesting topics to talk about, and you guys will also have some ideas, right? Okay. I will talk to I will also talk to Ansul and give him as a suggestion, but not sure like how the relevant will take it. But yeah, you guys like they will definitely listen your voices. I wrote first line in code in Solidity. Ah, very nice. That's good step, Ekta. Actually, yes. Web3.js or like moving like starting thinking about the Web3. It's definitely nice. Definitely great. Okay, guys. So we can talk about it. Solidity, so Likit, it's a language which we uses in Ethereum. You know, there is a Ethereum blockchain network which provides you the functionality of decentralized or distributed applications. Right now, a lot of talks are going on, right? Web3. So Ethereum is one of them, which works on the blockchain network. So Ethereum provides a language which is Solidity for creating dApps or smart contracts, all those things. Yeah, a lot of things are there. Ankit, Solana is also one part of blockchain industry. They also provide some coins. Yes, definitely, Deepak. A lot of places we are using the Lambda functions. And you know, earlier Lambda function was only related to AWS, but now Lambda function has been used very commonly because Python has also introduced the Lambda functions, And in JavaScript, arrow functions also work in a similar way as the lambda functions. And I know that I might be, yeah, like I think Ekta is saying Java is also as the lambda function. So that's why I think, when languages started using some terms, so it becomes very common. So that's why I think you were saying that a lot of company using lambda functions, because now it comes into the languages. So when languages, when in the when side when any terms come in language, so it's very common. In the same, I think lambda functions work same as the JavaScript arrow functions work. There might be some differences, but people says in the blogs that it's similar. Yes, serverless tech. Yes, that's the first thing when the lambda comes into the picture. You know, Deepak, with the serverless tech, there is one more thing has recently starting, that's called edge computing. Just try to search about it. Edge computing. That's little bit closer to serverless. Anyone is interesting, they can go for edge computing also. Just read about it. Do not go deep into that, but just read about the edge computing as well. That's totally little bit close to serverless tech. What especially Lambda has. We can talk about it, Parag, or everyone in like we can have a guest lecture or anything about that. We can talk about it. But yes, it has like very interesting things where you do not need any resources. You don't need to purchase any resources, and it will only work whatever you will use. Like whatever time that lambda function will work, that lambda function will use, you have to pay only that much amount, and you do not need to think about the underlying resources, underlying memory, underlying CPU. You do not need to think anything about that. You just you will just get you will just get some of the input or output. You just need to connect there, and you have to just pay for that much your function is running. Like you have integrated the function, but that function, like you have integrated for 1 year, but you are not using that function, so you will not pay it. That's the benefit lambda functions brings. So there are a lot of things in the cloud which are happening quickly. We can talk about it any other day or in one of the revision classes. That would be the great place. Okay. I'm still using the Node.js as in my language, and in the technology I'm using right now the CDNX. CDNX graph. I was before March I was using the GraphQL. After that I'm using the CDNX right now. With CDNX I only get to know about these actually the edge computing. So that's why I told you read about. I'm also reading about the edge computing. I will share in LinkedIn if you guys interested there. Sure. Okay, guys. So now let's move into today's session. Otherwise, these talks can never end because every time new terms come, so we can just continuously talk about it. Okay, so let's now quickly revise it. So we can just refresh our, when we say revise it, it means bring all the things from your disk memory to the cache or RAM, and then we will continue our discussion. Okay, so let's start from first slide from the previous class, and we will just go quickly. If you guys are stuck somewhere, I will just talk about it a little more. Okay, then let's start from the first slide. You guys are able to see my screen, right? It's already shared. Let me know in the chat. Yeah, thank you, Vishal. Okay, guys. So how we started? So we have started talking about trees with some examples. So we have taken first example. I remember directly. I have shown you the tree, and I have shown you that this tree has some of the terms which are very popular in the computer languages as well, like the root, like the branches, right, and like the leaves, right. The similar terms we use it here as well in the computer level trees as well. Then another example I told you about the trees, that was the family structure, right? In the family, as we have grandfather, then we have parent, then we have child, right? So in similar way, we design our trees in our computer trees also designed in a similar way, right? That was the second thing. Now the third thing, which was very important, and that is we whenever we are designing anything or solving any problem, we always try to break that problem in smaller parts, then again break it in the more smaller part, and then when we like after dividing it, when we like reach to the at the end where we cannot further divide it, we start solving from there, and then we go little bit up, and then from there to top, and then from there to the root. And then at the end we solve our problem or design any solution. So you can see that everything whatever we are doing, even in the computer or is outside as well, we can somehow break that into trees. So that's why the trees are very important, like data structure, which are used in many ways in the computer systems. Lot of problems might be some of the the JavaScript things. Lot of JavaScript things. Like when I'm talking about JavaScript, so in JavaScript prototype chain, right? Their object, the top class, or the root of JavaScript is the object, right? So object is also internally designed in a tree structure, where in the object we have function, we have arrays, and then we have self object, something like that, right? And then we have other things as well with the objects. So similar way, like why I'm telling this thing. So like when you're designing any solution, like some problem is coming to you in future in any interviews or in your organization, you can think that somehow the tree's data structure could be used in many problems. And guys, while you're using tree is the outer view. If you just go a little bit deep into the tree, you will see that you going to use other basic data structures as well, like the queue, stack, array, linked list. They are all behind the tree. So that's why tree comes into the front, and then you will see at the back end everything whatever you are doing, it's going to happen with the stack, queue, and linked list. Okay, so that's what why I'm telling all these things. I just want you guys to visualize it in your mind, that how much importance tree has in the computer system. And when you got any of the problems like that, you can also think with the structure of tree. And now if we talk about the structures, so that's how a tree structure looks like. You can see in my screen, always there is a root node will be there. Root node is also known as the parent node, and root node is also known as which does not have any parent. It means that's the first node in our tree, right? That's why we are saying the root. A tree also has first root, then tree starts, right? So that's what the root is here. Then in the root we have parent, we have child, we have siblings, we have sub trees, right? If I just go to the next slides, you can see here also siblings are there, sub trees are there, then labels are there. Then we talk about depth, then we talk about height. All these terms we have talked about in the last class and previous class as well. From the, I think on the Monday or before that, I think, yeah, on the Saturday, yeah, on the Saturday, oh, sorry, on Friday, I remember. Yeah, on Friday we have discussed all about these things as well. Okay. And then guys, after discussing these terminologies, so even class represents some sort of trees, like classes, properties, and behavior. We access when using objects. Uh, uh, See, the class. mm, we can create a class of tree, that I can understand. But if you just simply want to talk about a simple class, so that could not come into the tree actually, because mm, because they are not connected. See, you have one class, you create one object out of it, right? That object will have only these properties and behavior, correct? But you cannot connect them with other objects. You need to like create some relation externally to make the connection between them. So that's why I'm thinking little bit about classes. Can they come into the trees or not? But yes, one class is specifically, if you want to say, that could be one class, that could be tree. But yes, again, see, uh, one class has one property, it cannot go further into that. It has one property, it can have multiple properties like that, right? But there could not be another tree we cannot create with the class. Are you getting it? Like if there is a student class, then in student class there will be ID and roll number, and then we have the like class or like section. These three properties will always be there. Now we cannot create anything else with these three properties. So that's why classes could not fully fit into the tree part. Okay. Okay. Yeah. Yeah, it's a little bit different. Okay. So yeah, after that, guys, what we did, so now we have the visualization of tree. So now what we did, now let's define, because the trees could like go into the multiple levels. As I was saying, right? Trees, because in the linear data structure, you are running in one level, right? Only. But when we are talking about trees, these are non-linear data structures. They can go into multiple, like at one place, from the one point, you can go into the multiple directions, right? So that's what, if we have multiple directions, there could be difficulties, right, in traversing those things or finding out something out of it, right? So those are some difficulties with the trees, right? I'm not saying these are the complexities or these are like the disadvantages of trees. These are advantages as well, because in the graph, in the real life, we always have multiple possibilities, right? Like as a career, I can go into multiple careers, right? Like I can choose multiple careers. So in real life scenarios, there are always multiple scenarios. But if somehow we can reduce that complexity, so we can quickly or fastly we can traverse that tree, or quickly take the decision, right? If you have only two decisions, you have to join Amazon or Flipkart, like Amazon or, yeah, Flipkart. You have to join only two organizations. You can quickly make the decision, right? You have to just you have to search little bit less, right? But if rather than that, if you have multiple choices there, Amazon, Flipkart, Meta, Google, these, that, now you have bigger difficulties, right? Now you have to spend a lot more extra time to decide or make decisions, right? So that's what when we have less, like some restriction or less choices, we can do some operations quickly. So that's why we have divided our trees and try to reduce their branches. And then why we are doing that? So getter to, because we can get a smaller search space, so we can do quickly operations. So that's why you can see we have divided our trees into binary trees, right? There is very, like, binary tree is the very famous examples or important example, I would say, in the trees, because it a lot of problems we have seen which are solved with the binary trees. A lot of places like heap, or I've already told you about the heap or object structures. A lot of things we are creating with the help of binary search tree. And there is binary trees, and there is binary search tree that we will discuss in our next class. Binary search tree, that also we create with the help of binary trees only. Okay, so that's why we are reading about the binary trees. That was the purpose why people has given the invention of binary trees. Okay, now let's talk about what is binary tree. Okay, so what is binary tree is, guys? So binary tree is just very simple definition. They are saying that in a tree, in a tree we will say that that tree is going to be binary tree with where any node, you know that a tree has nodes, right? So if you guys want to see the nodes, I will show you also. A is a node, B is a node, C, D, these are known as the nodes here, right? So now they are saying that in a binary tree, any node can have two child nodes, can have can have almost two child node or max two child node. Means they can have zero child node as well, or, yeah, at most, yeah, zero child node or one child node or two child node. These are the three conditions. These are the constraint they have provided for a binary tree. So now you can see that you like any real life scenarios also. Like I'm taking same example of like career. So like if I have to like job from any two companies, I can have offer from one or two, or from nowhere. So this is the situation. Correct. I have job offer from nowhere. So it means I do not have any further nodes. If I have offer from one organization, so I have one node. Because I am right now the root node or the parent node, I can say. I am considering myself as a node. I can have only two, I can have maximum two decisions here, or two choices. That's what the binary says. Binary tree says that. That was a simple definition for binary trees. It can have or at most two childs. It means at most means or max two childs. Max also the right term is max. When we say max, it means 0, 1, or 2. That was the condition for binary trees. Now binary tree has also some more restrictions there, right? In binary tree, there are some more types up there. types over there. We already talked about the label, depth, and height. So I'm not going to talk about it. I'm just moving into the types of binary. There we in these three types we were confused. Like full binary and perfect binary we have already understood, but in the complete binary we were confused, and like I was confused, not you guys were. Like it was completely confirm about it, but I was confused. So I read it about it. So before moving that, so let's complete the full binary also. So one of the type of binaries is full binary. And in the what was the condition for full binary? So the condition for full binary was it can have only zero child or two childs. Let me check 1 minute. These conditions for the full, yes, zero child or two childs. That was the condition only for full binary. Correct? So we were good with that, right? That was the condition for like any tree you can take if it has zero child or two childs. It cannot take one child. Correct? If it is taking one child, it will not be it will not be said as full binary. That was the constraint for full binary. Now the last one, perfect binary. Last one, the perfect binary. So we will talk about the middle one, but let's talk about the last one. Navneet is saying full 0 and 2. Full is 0 or 2. 0 or 2. Not 1. Because see, in the binary, we have 0, 1 or 2. 0 or 1 or 2. But in the full binary, we have only 0 or 2. Correct. And then finally, sorry, in the perfect one, in the perfect binary, it is saying all the intermediate level should have two childs. All the intermediate level should have two child, and last levels, at the last level, all leaf node should be at the same level. All leaf node should be at the same level. Correct. So let me show you very quickly the example also. So we can quickly see the example. Correct. So if this is our root node, these are going to be our intermediate labels, right? Right. So you can see, guys, these are all our intermediate labels, right? So all the intermediate label should be have two childs, and at the last level or all the leaf node, you can see these are the leaf nodes. Leaf nodes are those nodes which does not have any left and right child, right? So leaf nodes, all the leaf node should be at the same level. That was the condition. That was the condition for perfect binary. Okay. So full binary we have covered, and then we have covered the perfect binary. Now there was the middle one. Which one is also known as complete binary or almost complete binary. Correct. That was the second one, and in that complete binary we were confused with the second condition. So the first condition was same. All the intermediate level should be filled with all be with two nodes. All the intermediate level should be filled with fully filled. They were saying in the lines they should be fully filled. So fully filled means they should have two childs there. Correct. And the last condition was the at the last level or at the last or all the leaf nodes, they should start from left to right. We should start filling them from left to right. And in the last class where I was confused, I have not read the right part. I just understood I have to start from left. I should not be starting from right. That was the problem. That was the confusion which I had in my mind in last class. So that's what, if we see the example of almost complete binary, guys. So if we have this structure, you can see these are internally filled now. So you can see if I'm just putting like this, this is my last label, right? You can see these are all intermediate labels. They are good. They are fully filled. Correct. If this is my last label, so last label or the leaf node, they should always start from left to right filled. Left to right filled. So what does it mean? So whenever I'm filling this thing, I should start from left then I should go for right. Then I should start from left, then I should go for right. Then I should start from left, then I should go for right. Then I should start from left, then I should go for right. That was the correct almost complete binary tree. Almost complete binary tree. And that's what the Likhit was also trying to tell in our last class. Okay, because in the last class, what mistake we were doing? The mistake which I was doing there in the last class, it was this. I was thinking like this, and this could be fine because we are just filling on the left side. But this is wrong. We should fill that particular node from left to right. From left to right. This particular root node should be filled from left to right. And that's why we have to first fill this, then we have to go for this. Now it is almost complete binary tree because we have already filled left to right. We can leave this one. So how is it? You can see, Vishal, this one is also almost complete binary tree. This is also almost complete binary tree, but this is not the perfect binary tree because in the perfect binary tree, all the leaf node should be at the same level. But you can see here, all of the leaf nodes are not at the same level. Understood, Vishal? So, like the purpose of almost complete binary tree is to make a tree a perfect binary tree. Almost complete binary tree, if we just fulfill the condition of almost complete binary tree, and if we fill all the nodes, then almost complete binary tree will automatically become the perfect binary tree. As you can see in this example on the top, you can see this almost complete binary tree. As we are filling from left to right, it automatically becomes the perfect binary tree. Understood, Vishal? Guys? Okay, so are we good with are we good now, guys, with these things? These are the three types of binary trees which we, yes, there is one more, guys, which is called skewed binary tree. There is one more binary tree comes which called skewed binary tree, where the definition is Suraj is saying repeat. Okay, so Suraj, the perfect binary tree, we are good, right? With the perfect binary tree, we should have the internal fully filled and the leaf node that should be at the last level, right? And in the almost complete binary tree, just the one difference, and that difference is there's the difference between perfect binary tree and almost complete binary tree is that the leaf node should not be at the same level. First thing, leaf node should not be at the same level. And when we are talking about the leaf node, they should always, whenever we are filling the leaf nodes, they should always be moved from left to right. You can see left to right. So that's what, whenever we are adding a new leaf node, you can see we are putting from the left to right, and then we will go from there also. So there cannot be right like this. There cannot be a right like this. Before putting a right here, you have to put the left, and you have to put all the, and before that you have to pull all the nodes left and right, then only you can put the right here. Then it will become the perfect binary tree. Perfect complete, sorry, almost complete binary tree. Leaf node can be at most two for almost binary tree. Leaf node can be at most two. Yes. Zero is also here and two is also there. Yes, 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 Joseph. Leaf node can be almost two for almost binary. Yes. And that same goes for perfect binary as well. Are we good, guys? Let's understand with examples. I think with examples, do not go in the words. Understand with examples. What happened? One minute, guys. Okay, so some. Why it is not working? Let's choose it again. See, let me take a new page then. Okay, I need to close it then. Yeah, remember we did it first one time. Let me open it again. Let me see 1 minute here. This is what I understood from the almost complete binary tree even. Okay, let me show you the difference with the example, Vishal. Oh, it's taking a lot of time. Let me stop. Docker is running. That could be the reason. 1 minute. Quit Docker. Quit VPN as well. Yeah. Okay. So let's see. Yeah, it's still that much speed, but yeah. Guys, can you tell me this can be our most complete binary tree or not? Anyone tell me? Everyone tell me this could be our almost complete binary tree or not? No, right? Why? Why it is not our complete binary tree? Because guys, we have to start from left side. We have to start from left, all like in the last node where we are filling our leaf, we should start from the left side or the left node, whatever the left node is there. So we should start from here. Now here, now is it the absolute complete binary tree or not? Now I added the left. Now I added the left. So I started from left. Can it be a now? Now per almost complete binary tree? You just see, guys. You just see it. Can it be now the almost complete binary tree? No, right? It still cannot be almost complete binary tree because the almost complete binary tree condition says that whatever node you are filling at the last label, it should be left to right. Left to right. That whole node has to fill left to right. So first we have to add one node here, one more node here. Now, can it be almost complete binary tree or not, guys? Can it be almost complete binary tree or not? Yes, it can be now because we have added the last, we have started adding from the left side and we have completely filled left to right, and then we are moving to the left side. Then we are moving to the next node. Understood? Now, can you guys tell me, is this the perfect binary tree? Is this the perfect binary tree? No, right? It's not. Why? Because all the leaf nodes are not at the same level. All the leaf nodes are not at the same level. You can see this is one leaf node. This is one leaf node. These are at different levels and these are at different levels. So that's why this is not the perfect binary tree. That's the difference. Yes, not at equal level. So now you guys got it. Vishal, Suraj, whoever was asking, whoever was having some doubt there. Are we good with that now? With the examples? Yeah, I think with the examples, it creates a little bit more clear. Great. So now let's move into the next part, guys. Full binary tree also with examples. Okay. So full binary tree with the example. So let me ask. Okay, guys, let me ask to everyone. Can this be a full binary tree? The second one, guys, you have to see this one. Tree 2. Can this be a full binary tree? No, right? Why? So Joseph is saying yes. No, Joseph, it can't, because the full binary tree condition is it can only have 0 or 2 nodes. 0 or 2 nodes, 0 or 2 child's node. And you can see here, it is also having the 1 node. It is also having the 1 child node. So that's why this is not the full binary tree. So, if we add one more here, so now it becomes the full binary tree. So now it becomes the full binary tree. 0 or 2. Yes, 0 or 2. That's the condition for full binary tree. Yes, it's perfect too. You can see that, guys. All the intermediate nodes has the already filled or has 2 childs, or all the leaf nodes are at the bottom. It's the absolute complete binary tree also. It's all the trees are here. Binary tree is also there. Full binary tree is also there. Everything is here. Are we good now, guys? Have you understood these differences totally? Okay. Now let's move into the next part quickly. See, this is good actually. You guys are visualizing. No need to, remember everything. Just visualize it. Once you will visualize it, it will very helpful in solving the problems as well. Okay. So now let's move into the next part, which was the traversal part, right? Implementation parts are we can implement with the help of nodes or array as well. So that's fine. Let's leave that. That's not much important. We are going to use everywhere the node scenario. Okay. So now let's talk about the traversal, guys. Okay. So we have 3 type of traversals: pre-order, in-order, and post-order. For pre-order, sorry, we have 2 types of traversal, which is DFS. Second one is the BFS. And in DFS, we have 3 type of traversal, which is pre-order, in-order, post-order. Correct? And in the BFS, we have only one traversal, which is level order traversal. Right, guys? Are we good with that? Though all those 4? Anyone wants to know about the logic about it, or should we start solving one problem? I think we should start with solving one problem, and then we should see that. Okay, so let's jump into the problem directly, and let's understand all 4 from there. Okay, something is not working properly for me, guys. Okay, no problem. So let's quickly take a tree, randomly tree. I'm not taking any specific, I'm just taking randomly, so you guys can just better understand some of the things. Not repeat any till not repeat. I'm just trying to not repeat anything. 14, we can repeat it. That's not case 5. Yeah. Okay. So so guys, this is our tree, right? And now you already know that a tree has multiple subtrees. A single node can also be a tree. Am I right, guys, or not? A single node can also be a tree. If I create simple 5 here, this is also a tree, right, guys? This is also a tree, right? So see, guys, in each of the tree, we have 3 things. We say that 3 things. Each node has left or right, and this is called node/root. Always remember these terminologies, guys. Always remember these terminology, because these terminologies are going to help you a lot while solving your problem. Correct, guys? So each node can be a tree. Each node can be a tree or subtree. Correct? So now, while traversing, when we talk about DFS, when we specifically talk about DFS, so you know what we do in DFS? DFS full form is depth first search, right? So what exactly it says that you have to choose any of the branch or any of the sub tree in a tree, and then go deeply into that, and then go deeply into that, and then try to pick element from there. When you reach at the end of that branch, then start reading from there. That's the meaning of DFS. Correct. And then if we talk about BFS, if we talk about BFS, so BFS is breadth first search, or you can simply, you can understand, like you have to start like looking into each branch of that tree, each branch of that tree, and then slowly you have to go down. You have to start from top, and whatever branches are coming first into your, while you are going down, because you have to traverse, right? You have to start from the top of tree, from the root, and then you have to go down. So BFS is like branch wise traversal, you can say, level wise traversal or branch wise traversal, whatever you want to say. So you have to like continuously look into each branches, and whatever elements are coming there, you just look into that one. So see guys, let's just like I'm just trying to visualize this thing to you guys. So just consider this is a tree. Just put a line between of them. This is a tree. This is a one branch. This is a one branch of a tree, and this is another branch of a tree. You're getting it? This is another branch, you can say. So now what we'll do in the DFS, when we are talking about the depth first search, so we will first go into this branch depth. We'll reach to the end every time. In all of the DFS, you will see we always goes till the depth, and then we start coming back from there, and then we go into the another branch. That's how we are doing it in the DFS. First we go traverse everything here, then we go into the right side of that tree. Am I right, guys? That's how we are doing the DFS. But in the BFS, we divide our tree. We divide our tree like this. Let me just clean these things. Yeah. So in DFS, we again have this tree divided from here, and then we divide it like this. This is first branch, this is second branch, then this is third branch, then this is fourth branch, this is fifth branch. That's how we do the division. That's how we traverse it. These are two different ways to traverse a element. Are we good, guys, with these? Understood how the DFS and BFS is visual, like in visualization, how it is working? Okay. Now let's jump into the parts of DFS. Now let's jump in. See, guys, in last class we were just talking about so many things, but today I'm just revising everything whatever we talked. So goes into your mind, and you never forget about these things. That's why I'm just trying to visualize everything whatever we have done in the last class. Again, let's try to do the pre-order, and now let's try to understand the traversal parts of under the DFS. Okay, with the same example. So two things we need to remember first. First thing, a tree has multiple subtrees. A tree has multiple subtrees. Can everyone visualize it or not? First, tell me, can everyone visualize it or not? This tree has multiple subtrees. Can everyone visualize it or not? Let me know in the chat. Can you guys visualize it, or you want me to visualize it? I can show you. You can quickly see that this could be one subtree. This could be one subtree, the bigger size. Now let's extend it. This could be one subtree. So that's why I'm saying every node is a subtree, and then you can see as we increase some more nodes, that could again be one subtree. So you can see here why I'm showing you, because it tells you how to do iterations or how to write your recursion functions. Okay, because in the tree they follow this subtree concept there, and the concept is every tree has multiple subtrees. So you just need to traverse those subtrees, and you will automatically get the answer for the bigger tree. So that's the first thing you need to remember. And second thing, in the DFS, whenever somebody was talking about the DFS, you need to deeply go into any of the branches. Okay. So now let's jump into the the pre-order. We have already covered it in last class. So let's start with in order. Okay. Anyone have like I will quickly show you, but anyone has any doubt in coding of pre-order in iteration? By with the iterative way, also we tried. Anyone has any doubt on that, or we are good? So the code ones, what will happen with code, Parag? Hey, you guys, like, see, this is not good. Whenever somebody was saying to you that you remember about those things or not, you should look into your mind that you remember the logic about it or not. If not, then I think you need to like read about it again, right? So let me tell you again, let me explain that logic also, then we will know for that. You know the logic. Okay, know the logic, then I think code is not necessary, right? Okay, we push first right node, is that one, sir? Yes, we push the first right node. Yes, that one only. But no problem. We'll start. Okay. Let's start from the pre-order then. Let's quickly finish that because we already know that. So let's quickly finish the pre-order first. So in DFS we have three, right? Pre, in, and post. We have three. And how we have learned the logic for them? In the pre, root would be at the first, then left, and then right. In the in order, root will be in the middle, and then left and right in the same way. In the post, left, right, and then root. That's how we remember it, pre, in, and post. And now let's talk about the pre-order. So in pre-order, how we were calculating it? You can see in the pre-order, we have to first print our root, and then we have to go for left, then we have to go for right. Correct? So in the pre-order, you can see this is our root, right? So because this is our tree, I can see this is bigger, like the main tree. So now our root would be 1 here. Correct? Now we'll go into the left side. You can see now we are going to left side. So once we go into the left side, now this become our whole tree. You guys are able to visualize it? Now this become our whole tree. Again, now because this is again a subtree, we need to apply the same logic again. Root, left and right. So now the root would be 3. So we'll print a 3 here. Again we'll go into the right, again we'll go into the left side. And 7 is here. You can see guys, I'm just going one by one deeper. You can see one by one I'm going just deeper there. Now you can see again. Now this has become our tree. 7, 14, 5. The third tree. Correct? So now 7 is at the root. So 7 I will be printing out. Correct? 7 will be printing out. Then I can see there is no, once I printed out the 7, I will go into the left side. You can see the second step is left. There is no left. So I will go into the right side. Yes, in right side, I have again one subtree, which is the last, this one. Again, I will print out the root, which is 14. And then again, I will do the same thing, left and right. So yes, I have the one element at the left, which is 5. Now I do not have anything at the right side. I do not have anything on the right side. So what I will do, I will start going back. And I will start going back and I will come back to 1 only. Because we were traversing the bigger tree, right? We were traversing the main tree. So now we have already traversed everything on the left side. We got the null. So now we'll come back to this part. And now we'll go into the right side. Now we'll go into the right side. And again, we'll see that. Again, now on the right side, we have seen it this subtree, this bigger one. Now again, we've seen the root, which is 5. So again, 5 will come here. Let me do it 6, guys. So there will not be anything repeating. Otherwise, you guys might be confused which 5 is that. Right? So let's move it to 6. Correct? Now the root, there is no left. I will go for the right side. So 9. This is again our tree. Now there is no, this is our root. Again, we'll go into the this subtree. We'll get 10 and we'll get 11. We have already done this. So 8 was missed. Okay, 8 was missed. Where was 8? Oh, yeah, this was the 8. So after 3, This is a route. We went for left 7, okay, 14, 5, and 8. Yeah, after 5, 8 will come. Correct, because we were traversing this tree. So after 5, 8 will come. So 1, 3, 7, 14, 5, 8, and again 5, yes, 9, and 9, 10, 11. Correct. That's totally right, Likhit. So everyone understood the pre-order logic? Correct. So now let's look. So now you guys can see that what I'm doing, I'm continuously following some steps, which are print the root. I'm talking about the recursion way. Print the root, go to the left, and do again. Go to the left, print the root, 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 and once the left is nothing there, then go to right. Can you guys see that? Am I following the same step or not? First, print the root, go to the left. Again, print the root, go to the left. Again, print the root, go to the left. If not, if let me, yeah, yeah. Here we can. If left is no, let me just erase it and write it little bit better. Yeah. So if left is not null, if left is not null, then follow step 1. Follow step 1. Follow step 1 and 2. Follow step 1 and follow step 1 and go to left. Yeah. Follow step 1 and go to left. That's what. And if left is null, go to right and follow step 1. Yeah, I think this could be the right line. Follow step 1. Correct. We can correct this one. If left is not null, then go to right, go to left and follow step 1. Follow step 1. I think yes, these three things we are doing, guys. So first, print the root, which is 1. Then go to the, if left is not null, for this left is not null, go to the left, follow first step, which is 1. Follow first step, which is print the root. So we are printing it 3. Then again, if left is not null, go there, then do the same thing. And if left is null, if somehow we got the left is null, then go to the right and follow step 1. That's what we are doing, guys. These 3 lines continuously we are doing. So is it not look like a recursion where we are continuously doing the same step again and again for different values only or for different trees? Am I right, guys? That's what we are doing. So that's why yesterday we have written the function something like this. The same lines we have written there. Pre-order, or this is our node or root. We can say this is our root. Correct? So we have written a function like this. So first, console.log or print root.value. Correct? And then what I was doing, I was again calling the pre-order because I want to go for the left side, root.left. And this will only happen when root.left exists. If it is null, then do not do that. And once all the left is done, then go for root.right for the same root. Pre-order root.right. Guys, can you see that? For this 3, we have first traverse everything on the left. 7, 14, 15. You can see 7, 14, 15. Then we went for 8. So that's what you can see. Till we are getting the root dot left, continuously traverse there only. And once the traversing of left is done, then go for right. Then you can see we have printed out the 8. Are you guys able to visualize it or not? Because the very important thing is visualization here. Yes, the Inception way. Yes, the Inception movies, if you are talking about. So yes, inside one, we are going into the next one. So you can see here also, In the pre-order with the recursion, pre-order is not there. Okay, that's fine. Here pre-order recursion is not there. In order with recursion is there. That's what you can see here also. We are continuously see this is about the in order. So that's why first we are printing the left. We are just directly going to the left. Then we are printing. Then we are traversing the right. But in similar way for pre-order, we will first print. Then we'll go into the left side. Then we'll go into the right side. Are we okay with that? Are we good with the recursive approach, guys? Everyone able to understood? Everyone I'm talking about. Joseph, Arad, everyone. Because visualization is important here. And you can see that's whatever we are doing in the code, that's what similar thing I've done here. Okay. So now let's talk about the very quickly about the iterative approach also. About the iterative approach also. So what we were doing in same we will do in the iterative approach also. So we'll start from this element, the root element, and we have to print this one. So we have to print this one. Correct? That's the first step. So what we'll do, we'll take one stack. We'll take one stack. Okay. And then in this stack, first we'll keep our root node, which is 1, right? Which is 1. And because we have to first print it, so that simply we will take it out. We'll take it out. And this could be our answer here. So we'll take it out and print it 1. After that, we have to go for the left side. After that, we have to go for the left side. Correct? So guys, you can see I can directly push the left element here also. You can see this one has two things, 3 and 6. 3 and 6. Correct? So if I will push, because one has been already popped out, so if I will push 3 and then 6, so you guys can tell me which one will go out first. Which one will go out first? 6 or 3? It will go 6, right? 6 will go out. So that's why, but we want 3 first. We want 3 first. So that's why we will insert in first we will insert the right side, then we will insert the left side. So now you can say 3 will come out. And then again, for 3, we have to follow the same logic. 8, 7. Once the 3 will come out, we will insert 8, 7. So 8, then 7. You can see first right side, then left side. You can see 8 and then 7. Again, now we have to traverse the 7 because we have to traverse because see, whatever we have to traverse, that is the left side. That we need to keep on top. Whatever we need to traverse, you can see in the pre-order, it happens what? Root, left, right. Root, left, right. So whatever we need to traverse after root, that we need to keep in the top on this stack. That's what you need to remember. Okay, whatever we need to traverse after root, that element has to come into the stack top. And how will do that? You will do that first. You will push the stack dot right, sorry, root dot right, then you will push the stack dot left. Are we good with that, guys? Now, and you can see the code also. If you guys want to see the pre-order with iteration, yeah, it's here. Pre-order with iteration, you can see in the stack continuously loop is going on iteration, and I'm just stack.pop, taking it out and pushing first the right, then the left. This one is very easy, but the other two are little bit complicated, guys. In order and post order, little bit complicated. So are you guys understood first the in pre-order? Then we will jump into the in order and post order. Are we good here? Anyone has any doubt? Any questions? Okay, so we are good here, right? So now let's go for the in order. Now let's go for the in order. We'll take the same example there also. So 1, 3, what was there? 7, 8. We'll take the same example, guys. No problem. 8. Take the 6. 14 and 5. Quickly Calculate in order for this, guys. Quickly calculate in order. 9, 10, 11. 9, 10, and 11. Quickly calculate the in order for that, guys. The formula is for in order is left, root, and right. Left, root, and right. Quickly calculate it. Ekta has calculated it. What about others? Guys, are you trying it? As you can see, in the in order, we have to directly go to the left. Then we need to do the printing. Then we need to go for the right. So right, the recursion logic is very straight. Print, sorry, the recursion logic is very straight. Go to the left, print, and go to right. Correct? That's the same logic. That's the simple change in the recursion function. And let me now write the numbers in the in order traversal. So it would be, we'll start from this. We'll go into the left side, which is 3. We'll go again to the left side, 7. We'll again go into the left side. We will not get anything. We'll not get anything. Get anything. Then what we are doing, we have to do the print here. We have to do the print here, which is 7. Correct? Now we go to right side. Now we go to right side, which is 14. Then again we'll go into the left side, which is 5. So now we'll get the 5. Correct? Because we do not have anything earlier than that, because it is at null. So we do not have anything. So now what we need to do that? We need to move back. We have to check into the right side. Do we have anything in the right side? No. Now we'll go back to the previous node from where we started. So this is the 14. So we will print it. Then we do not have anything in the right side. We'll go on the previous one where we have 7. Correct? So now this one we have already traversed. The left, the right, we have already traversed. Now we'll go into the 3. Right? So we'll first print 3. Then we'll print 8. Then we will print 1. Right? The root node. Then we'll go into the right side, 6. We do not have anything on the left side. So we'll print the 6 here. Then we'll go into this one. And then to the left, 11, 10, and 9. I hope your answer is matching with this. Let's see that. Sir, we'll start from 5. So Ekta, like 7's right has 14. 7 right has 14. And then we are going for the 5. 7 right has 14. So it should start from 7, right? Because 7 does not have any left. Am I right, guys? Did you guys have any confusion with this? Because you can see that 7 does not have any right left. It is null here. So when we do not have any left, what we do? We go for root and then print it. 7. Then we go for the right side. Right, guys? Likit, yours is also not correct. Did you also mistaken that one? The 5 one you were thinking it is on the left side? Oh, okay. Yes, I think in the visualization it's little bit okay. Let me correct it. It looks like this is 5 is there. Let me correct it. No problem, guys. So it is like this 14 and then 5. Now it will make more sense. Right? Earlier, actually, yeah, 5 was coming down to that. So it could be, yeah, you guys were thinking that, yeah, 5 could be there. Yeah, 7, 5, 14, 3, 8, 1, comma 6, 11, 10, comma 9. Totally right. Totally right, Ekta. Totally right. Okay. So now, guys, now let's think about the iterative way. Now let's think about the iterative way. Okay. So we will take first a pointer or a variable which is current node. where we are in the current node. And then we will take one stack here. Okay, guys? So we will take the two things here. Okay. So now we'll start from the top. This is our current node first. Okay. So current node is at 1. Right, guys? So current node is 1 and we will insert it into a stack as well. So this is 1. So now you can see, according to the logic, what I need to do? I need to simply go for the left side. I need to simply go for the left side. And wherever guys, left and right is null, which is known as leaf node, wherever I got the leaf node, I need to print it. I need to print it. Correct? Wherever guys, I didn't find any left or right, that would be my root element. I need to print it. Correct? So that's what we are going to do, guys. We will continuously traversing this, and whatever elements are coming to the middle, we will put them into a stack as well. So now you can see, first current node left is 3. So we'll first push 3 here, and we'll change our current node to here. Now our current node would be here. I'm just writing current node as a C, guys. Okay. Current node as a C. And I will remove the current node from here because this is the first left. Again, we have to go to the left. Till we do not find any left, we continuously have to traverse to left. Again, this is our left. Correct? Now we are at the 7 and we have inserted the 7 here. And now our current node is at 7. Correct? Now, what we'll do? We'll make our current node to again. Again, we'll make our current node to current node dot left. So now our current node will be, see, first current node was 1, then current node was 3. I'm traversing values here. Then it becomes 7. Now our current node will be here. Oh, let's see, write C simply. And then the current value would be null. Am I right, guys? Till now you guys have understood or not? Current node will be pointing out to null. Everyone okay? Everyone. Current node is right now pointing out to null. So Suraj, we are just simply traversing to the left side. So we started current node from 1, and then whatever, we are just simply traversing to the left side. So current node dot left. Then we are finding 3. Then current node dot left, we are finding 7. Then current node dot left is null. At null, we will stop it. At null, we will stop it. Because now we do not have any further current node dot left. Got it? Everyone got it? So now, once we got our current node as null, what we'll do, we will take the top element from a stack. We'll take our top element from a stack and print it. So we'll take the top element from stack, and I'm writing an answer also, and we'll print it. So 7 is our answer. Correct? Now, and see guys, whatever element we are taking, we will consider that as my current node. So these are already done. And after null, I have make my current node to 7. Correct? You can see, guys, I did 2 steps. Once my current node become null, just remember this thing. Once my current node will become null, what I did, I taken the top element from a stack and put it into my answer. And then I made my current node to that top element. So now my current node is again become C, it becomes 7. This is my current node. Pop and print. First we did the pop, then we did the print, and then what we did, the popped node, whatever we have taken the popped node, we have also put it as a current node. Why we did that, guys? Why the third step we did? Because, guys, the formula says left, print, or right. Left, print, or right. If I consider 7 as my simple tree, so we have gone to the left. We have already gone to the left. Now we are coming into the center as well. Now we need to go for the right side also, right? For 7, we need to go for the right side also. So that's why I made my current node again 7. So why we did that? So we can go to the right side. So now we will go into the right side, guys. Now we will go into the right side. So now what we'll do? I will make my current node to this thing. I will make my current node to this and push it into the stack 14. Again, now we are at this subtree. Again, same logic. Try to find out the left. In this subtree, try to find out the left. So now our current node will move from C 14. Right now current node was 14. Then because this node has left side, so now we'll make our current node to here. And now in stack 5 will be there. Am I right, guys? Till now, are we good? Till now, are we good or not? I know that this is little bit complicated, but you just need to follow the formula or whatever the new rules I am following. Formula is very simple. In every tree, in every node, you need to first traverse all the left. You need to first traverse all the left. Once you find it out, left is null now. Once you find it out that your left is null, you need to pop it, the top element from the stack. You need to pop it, the top element from the stack, and that would be your answer. That would be your answer. Then make that popped item to your current node. Make that, because current node is now right now null. Only current node will be null when you have already traversed everything into the left side. Then only current node will become null. Once your current node become null, what you need to do? You need to pop the item, put it into your answer, and the pop the item will be your current node. Pop the item will be your current node. Why we are doing that? Because our step says left, root, or right. So now left we have already traversed, make it null. Root we have already printed it out from the stack, and now we have to traverse the right side. So that's why now after after doing the left side traversing printing, now I'm going to the right side, and again I will consider my right side as my tree, and then again I will start the same step. Go to the left side, follow all the left side. That's what I did. You can see in this subtree 14 5, I just went to the left side again and I got the 5, and after 5, because this 5 will also have null, so again once the 5 is pushed, this current will come to null. Now you guys know that, right? What is the step? Now you guys know that. What is the step? Once my current node become null, take pop the top item from 5. Pop the top item from stack. Pop it. Pop the 5 and put it here. Again, once you pop it, make your current node as 5. This step is same, right? Make your current node as 5. Current node as 5. Current node as 5. Now you tell me what we need to do next step, guys. After we have come back to, after popping, we have already make our current node as a, we have already printed it out. You see, you can see, already printed it out 5. Now my current node has become 5 again. What I need to do now? No, yes, Vishal has said correctly. Go to the right side. Yes, that's what I want to know from you side. You everyone. Go to the right side. No. Do not go there. Go to the right side first. Because for every node, you have to go to the left, root, or right. You have not went for right side. So now go for the right side. For this node, go for the right side. So again, after 5, null will come. Again, null will come. Correct? Again, null will come. That's what I want to tell you again, guys. Do not jump into any step. Go to the same step you need to follow everywhere. So now you again go to the right side. Now you will see that again you are at the null. Again your current is at what? Null. Again your current is at null. What do you need to do? Tell me what you need to do. Once your current has become null, what you need to do? Same step, guys, which you did just before. Yes, pop top element from the stack, which is 14. Pop that top element from the stack and make that element as current. Make that element as current. Make that element as a current. Yes. Yes. Now what we need to do, guys? We have already come to the now 14. Now what we need to do? You guys tell me quickly. No, no, no. Suraj, already we have gone to the left, right? 5 and null. Already we have traversed the left side. Yes, we have to go back to the right. Correct. We have to go back to the right. Again, for this 14, we'll go to the right side. And our current will become again null. Our current will become again null. So now what we need to do, guys, again? What we need to do again? Once our current become null, yes, pop the top element from stack. And make our current element as 3. So now our current element will come here. You guys are seeing it? Like whatever whatever I'm doing now, it is just iterating again and again. Same step we are iterating. Now what we need to do, guys? We have came back to the current item. Now we have came back to the previous current item. What we need to do? Again go to the right side. Yes, again go to the right side. Again go to the right side. And once we are going into that, push it into the stack. Now this will be our current. Now what we need to do, guys? What we need to do, guys, now? Now we have a new element, 8. Yes. Now we need to go to the left side. We have already pushed it. Vishal, we already pushed it. You can see. Now we need to go to the left side, or a, which is null. Correct? Which is null. So now our current will be pointing out again to null. So you guys know that. I'm not repeating and asking it. We have to again pop it out the top item and keep it here and make my stack, make my current item as a current. And now you again know that we have to go to the right side, which is also null, and make our current as this. And we again need to pop that top item from stack, which is 1. And make our current item as 1. So now the current item will be here. And now what we need to go do, guys? We need to go to the right side of now. Right side of 1. Because we have already traversed the left side. We have to go to the right side of it. Yes. So now once we go to the right side, first push into the stack, which is 6. Move our current to here. Current is 6. Now again, we have to go to the, what we need to do, guys? Then go left. Yes. Then go left. And left is null. See, automatically you guys are now able to tell it. So now first pop it out and put your 6 here. Right? And then null will become, null current item will again point out to 6. Now you know that we have to go to the right side. Correct? So first push the right side here. Current item. And make your current item this. Now again, we are at the new node. We have to again go back to the left side. And once we are going to the left side, you can see first it will come here, then it will come here. And it will push all the elements. 10 and 11. It will push everything. Am I right, guys? It will push everything. Am I right, guys? Am I right, guys? It will push everything because everything is lying on the left side. Now, Now what we need to do? We are at, our current is at here. Again, current will go to the null's right side. Sorry, left side. And we have to start popping it out. So first 11 will be popped out. And our current will become 11. Then we'll go into the right side, which is again null. I'm also like fixing it here also. Again null. We'll pop out 10 as well. Then make our current as in 10. Current as a 10. Then we are again going to the right side, which is again null. We'll pop it out the 9 as well. 9 as well. And make our current to 9. Current to 9. Now there is nothing in the stack. We'll stop it here. Because there is no, we'll go into, see, we will again go into the null. It's not like that. We'll again go into the null. Right side of 9 will again go, because it could be right side could also have. And now our current will be here. So once our current is null or stack is empty, we have to stop it. We have to stop it. Was it interesting, guys? Suraj felt it interesting. What about others? Okay, so let me show you the code of it now. That is more interesting. Let me show you the code. You see, guys, current node is equal to this dot road. So this is the current node pointer. This one, this pointer current node. Now I'm just checking my while loop. Till this while loop will run once current node will become null or stack has become empty. Stack dot length has become empty. This current node or stack dot length is greater than 0. Any one of them become blank, and like once both of them become like this would be the scenario when current node is null and stack dot length is 0, then only my while condition will stop. Otherwise it will not stop. Otherwise this condition will not stop. Okay, then what I'm doing, if there is current node, so push it into the queue and then go into the left side. Current node is equal to current node dot left. So see, this continuously, these two lines will continuously run till you got current node dot left is equal to null. Till you got current node is equal to current node dot left. This continuously these three lines will run, because this if will only stop when your current node will become null. And when it will happen, it will only happen when current node dot left is equal to null. You can see in the current node, you are assigning current node dot left only. Correct? In the current node, you are only assigning current node dot left. So this current node will, this loop will continuously run and everything will be pushed into the queue. As you can see, in the starting, we were pushing everything, 1, 3, 7, everything into the queue in the stack. So that's what. Let me correct it. This is why we are writing queue. It's a stack. It's a stack, not queue. Yeah, so that's what I'm doing here in stack.push. And you know, guys, once it become null, once this become null, I told you 3 steps, right? First, pop it out. You can see I am popping it out. And second step, I am making my current node as the popped item. You know that, right? Whenever I'm pushing it out, I'm updating my current node as well. So you can see that that's happening. Current node is equal to stack.pop. And then I'm answering, then I'm also putting it as my answer. You can see after popping it out, I'm putting it into my answer as well. So that's what we are doing. And then I'm going into the right side. You can see current node is equal to current node dot right. So now this whole right side, of tree will become my current node. And then I will again start doing that. Go to the left side, push it to the stack, same step, whatever we are following. So this is the code. This is small code. You can see that, but it's very interesting code. Yeah, I've removed that queue. This is the 6 or 7 line code, but that yeah, that's why I removed it. You can see this is, see, if I show you directly this code, you will not able to understand. That's why with that dry run only you can understand now code, because you can see lot of places we are doing the current node is equal to current node is equal to. So you have to understand why we are doing everywhere current node is equal to, because current node is the important one, and that you only can understand with the dry run. You see, this is very small, like 6 or 7 lines only, and doing the proper in order. I find it out this very, like, this is a small answer. The minimum line to do the pre-order. Yes, this is exactly what we're talking about. Yeah. Okay, everyone okay with that? Yes, that's what. Whatever we wrote, that's what. Totally right. So first we traverse everything is the left side. And once we got the null, we are popping it out, assigning our current node, printing it out, and then going into the right side. That's totally right. Okay, guys. So now let's quickly look for the post order as well. Post order is also a little bit complicated. There are, like, if you will search into Google, one of our trees, could you please write in this code one for half of tree? Okay, everyone is okay. Joseph, we are just going for break. So in break, just try with yourself, and still you face any problem, we can discuss it after break. Okay, just try with yourself. Otherwise, we'll discuss it again. No problem. Okay. So right now, what is the time? So 9:30 is there. So we can all connect back at 9:45. Okay, guys. We all can connect back at 9:45. And after that, we have, see, we will cover the post order. I think post order is little bit tough than this, and this time actually I will also, like, whatever step I am doing, I will also show you the code there. Otherwise, this time this problem will happen. Like, once you understood the logic, you will be facing difficulty to understand the code. So this time in the post code, I will also show you the code and whatever step we are following. So it will be easy to interpret both things. Yeah. And after post order, we are going to solve some problems. So yeah, no, yeah. After post order, we are going to also see that level order traversal, and then level order is easy, and then we will try to solve some problems. So let's go for break and quickly come back. Is everyone back? Actually, I'm really, I think I came little early today. Yeah. So I just came for Joseph. Joseph, did you want me to go through the code and the example again? Is Joseph back? I think he's still doing lunch. He's still doing dinner. Yeah, Joseph is back. Joseph wants to see that. Got it? Oh, okay. Then we are good. So it's just simple. You can see this is our current node. We'll start from here. This is our current node. Then we'll go into the left side. You can see that's what we are doing 137. So that's and every time we are pushing into the stack as well till we got the leaf element, till we got left as a null, till we got our left as a null. So that's what. If you see the code, oh, I'm not sharing my screen. I'm not sharing my screen. 1 minute, 1 minute. Yeah, yeah, yeah. So see, as we are seeing in the current node, what we were doing, we were always traversing to the left side first. And once we got left as null, we are going to stop it and then we are going to print it. So what was the step? Go to the left side. Once we got left as a null, pop top element for the stack, make it as a current node, and then go for the right side. That's what happening in the code as well. You can see continuously current node is equal to current node dot left. Current node is equal to current node dot left. If there is current node, once we got current node as a null, you can see we are popping it out and assigning to the current node, printing that value, and then we are looking into the right side. Then we make our current node as a current node dot right. Then we start again same step. Stack dot push, look for left. If left is null, again pop it and do the same thing. So that's why whatever we have explained, same thing is happening there. Okay. So just practice it one or two more times. You will be see that everything is same. So now everyone is back. Can we go into the post order and understand that as well? Yes. And I hope Hariran, you have understood both things, code and explanation as well. Ah, great. So let's go for the next one, guys, which is little bit complicated, but I will try totally. Yeah, I will try and code also. So I will try to tell you guys in easy way. Okay. Let's quickly take a new page and copy everything from here. We'll take the same example. 1, 3, 6. But in meanwhile, quickly give me the post order traversal for this. 1, 3, 7, 8, 7, 8. Ah, where I'm going. 7, 8, 14, 5, 14, then 5. See, these are the link. Huh? 14, 5. Then we have 6, 9, 10, 9, 10, and 11. Post order traversal. You know that the rule is left, right, and root. Correct? So go to the left, go, go to the right, and then print the root. Correct? Till we do not have any left and right, then print the root. Otherwise, directly go to the left, go to the right, then print the root. So, can anyone quickly tell me the post order traversal? So post order traversal, please write in the chat, everyone. Do not see mine. Please write in the chat. Meanwhile, let me calculate it also. So go to the left. Okay, we have 7. So yeah, so first 7 will come. Then go to the right. Again, in this tree, go to the left. 14 and 5. Go to the right. There is no right. Go to the root, which is 14. Go to the again right. We do not have any right. So print the root. Go to the left, right, root. Left, right already done. Then we root is coming. Go to the right side. 6 is coming. Go to the left side. Nothing is there. Go to the right side. 9 is there. Go to the left side. 11 is there. Go to the right side. Nothing is there. Go to the root. 10. Go to the right side. Nothing is there. Go to the right side. Nothing is there. Print the root. Already traverse the right side. Print the root. 6. Already traverse the right side. Print the 1. Everyone is matching. 7, 5, 14, 8, 3. Why not 11, 10? Anyone has not given any correct answer? Okay, Parag has given a correct answer. That's totally right. 11, 10, 9, 6, 1. Arad and Joseph has given wrong answer. And same for Hariharan also believes. Yeah. Same for Vishal also. What happened, guys? Left, right, and root. You forget? Left, right, and root. Go, go to the left. Go to the left. Once you got left null, go to the right now. Take that value, go to the right. Once you got right as a null, take the value. Understood, guys? Everyone understood? Or you want me to explain the traversal logic first? Everyone understood? Are we good, guys? Suraj, Hariharan, are we good? Arad, yes. Suraj, what about you? I think Suraj is not back. Okay. Okay, guys. So now, before jumping into the code, let's look for some patterns here. Let's look for some pattern here, which will help you while writing the code. Which will help you while writing the code. So the first thing which we need to understand is that earlier in the in order, when we have left, right, and root, left, root, and right, we were also going to the left side, right? In the in order, we were also going to the left side, left side, correct? Agree or not? We were going to the left side in the in order also, right? And after that, once we are printed out the left element for root element, for the root element, what we were doing? How we were getting the root element? In the in order, once we reach to the left element, once we have printed out the left element, for the root element, we were looking into the stack and we are popping out the topmost element that was giving us the root element. Everyone agree? That's what happening in the in order one. Yes. Everyone agree? We were popping out and that was giving us the root element. But here there is one twist, and that twist is, guys, that root element we do not need to take it out, because our logic is left, right, and root. So after traversing all the left, we have to go to the right side. Then we have to take out the root. Seeing the twist here? In earlier scenario, it was left, root, and right. So we were easily doing it. First we were going to the left side, keeping all the elements in stack. And once we got the last left element, we were printing it out, then popping it out from the stack. And then that was the root element. And then we were going into the right side. But here in this post order, there might be some scenarios where root element, where we do not need to delete the root element. We do not need to delete the root element. And there might be some scenarios where we need to delete the root element. Am I right, guys? There might be some scenarios where we need to delete the root item. So as you can understand, there are two scenarios now for the root element. Every time we have to go to the right side first. Then we need to print the root element. Am I right, guys, or not? You first make the root the current. You first make root the current, go to the right, then pop the root out. But what happened, Vishal? If the right has a bigger tree, then that root has to stay. That root has to stay. Once we traverse all the things in the right side. Correct, guys? So guys, let me tell you, we are going to take two variables here. We are going to take two variables here. One is the current and one is previous. One as the current. We are going to take two variables here. One as the current and second one as the previous. Okay. And now, you know that the current will, like the previous will start from null and current will start from this node, right? This is current. Correct. So now there will be, see, every time there will be every time there are two things, right? We are going down to the tree or we are going up to the upside of the tree. There are only two scenarios, right? We are going downside or we are going upside. Correct. So when we are going downside, so like see, from 1 we are going to 3. So now our current will be this and our previous will be this. Am I right or not? When we are going downside, because in the post order we have to go to the left side only first. Left, right, root. So we have to first go to the left side. So now we are going to the left side. So this will become our current element, or this will become previous element. Correct or not? Everyone understood till now or not? First, everyone understood the root scenario, because in the root there are now two scenarios. One time we need to delete the root. Which part? Suraj, which part you didn't understood? Two variables where we are taking. Oh, that's the problem, huh? You're joining very late, Suraj. So Suraj, what we are saying here, within the in order traversal, we were just going on to the left side, and then for root, then we have to go to the root side, because in order is left, root, right. So for the root, we were popping element from the stack. Correct? That was giving us the root item. But in the case of post order, root, we do not need root item directly after traversing all the left. We do not want root, because post order is left, right, root. Left, right, root. So we have to first go to the right side. After traversing all the left, we have to go to the right side. And how will somebody go to the right? That person can only go through the root only. Guys, for everyone, from left element, if somebody wants to go to the right, if this is a tree, if this is a small tree, 5 and 4, and this is a 3, if somebody wants to go from 4 to 3, he can only go from the root side. Correct? He has to go from the root side. So that's why this time we can't delete directly root. So that's why, Suraj, we are tracking two variables. One for tracking root, one for tracking parent, or one for tracking the childs. Okay, that's why we are taking the two variables. So two variables are current or previous. So previous will always tell us the previous nodes. Okay, now second thing I told, we are going downside in the tree or we are going upside. So when we will be going for the upside, that would be this scenario only. When we are going to upside. So this is 5, this is 4, this is 3. So first we'll go from 5 to 4 because left, we are traversing left. So once we have traversed the left and printed out 4 as our answer, now we need to go back. And from here we need to go to 3. So now you can see this is going back, this is going down. This is going up, this is going down. Everyone understood going up and going down scenario, and why we need to go up and go down. Going down is simple, right? Whenever we are traversing left side, that is going down. And for going to the right side, in those scenarios, we need to go to up. Or up means to the root and then to the right side. Understood, guys? Yes. For going to the right, we need to go to up. Or from right also you will go to up. From right side also you will go to up because you need to print root also, right? See, your answer would be 4, 3, 5. So it means first you need to traverse the left, you need to go up, then you need to go again down. This would be 3. Then you have to go back again up. Then you can get the 5. So that's why two things you need to understand here. First, the route is we need to traverse our route very intelligently. For that, we are going to use 2 pointers, which is current and previous. Second thing, you need to go down and you need to go up. And that only you can understand with current and previous only. With current and previous. And then I will show you how. Okay, so now let's move further. Now let's move further. Okay, so see, how will you check? How will you check when you are going down or when you are going up with these two variables, current and previous? Anyone can tell. Just think about it 1 minute. Anyone can tell with the and see this scenario also, 1 and 3. Can you tell, are we going down or are we going up? How can we tell this? With these two variables are assigned in two nodes, can you tell me, are we going down or are we going up? So see guys, very simple. If current, see very simple. If previous dot next or left or right, anything, two conditions. Previous dot left is equal to current, or previous dot right is equal to current. You will always be going down. You will be always be going down. Am I right or not? You guys tell me. You can see that above also. If previous dot left is equal to current or previous dot right is equal to current, you will always be going down. Correct or not? Make sense? Always, anywhere. Does it make sense to everyone? If you guys are stuck in, like facing problem anywhere, just tell me right now. Otherwise, it will be very difficult if we move further. Then if you will ask it, it will be very difficult for you to understand. That's why I'm spending time here. You just guys ask it here. So Parag, for going down, I'm saying previous dot left is equal to current, or previous dot right is equal to current. If this is the condition is becoming true, then it means we are always going down, because always our current will be down and previous will be up. So the previous dot next, a previous dot left, or previous dot right, if any of them will becoming our current, we will always be on the always be going down. Correct? Now, for going up, condition would be current dot left is equal to previous, or current dot right is equal to previous, this would be going up. And now you, if you want to see that, so make it, your previous will be here and current will be here. Now you can see that previous dot 1 minute. Yes, current dot left is equal to previous, or current dot right is equal to previous. Yes, see guys, now you are going up. Which part, Suraj? See these conditions. These conditions are self-explanatory. I showed you the arrows also. Let me show you. This is for up. Black one is for up, and red one is for anywhere you can take. This is current. This is previous. This is for going down. When we are going down, it means our current dot next. Oh, 1 minute. This will be P, and this will be C. So everyone, when our previous, see, you can see we are going down, right? Going down means traversing to the downside, means 6 to 9. We are going 6 to 9, then 9 to 10. It means when always our previous dot next will be current. You can see previous dot left is equal to current, or previous dot right is equal to current. So whenever we see this condition, it means we'll say that we are going down. But if we see that this scenario, black one, this one, when current dot left become previous or current dot right become previous, it means we are going up. It means we are going from 7 to 3. We are doing backtracking here. And why we want to do backtracking? We already have the answer for that. Because we want to go to the right side. From the left, we want to go to the right side. That's why we will be going up. Now you understood, Suraj? Down and up. So didn't get the going up condition. So see that condition. You tell me this condition. This is the diagram, Vishal. So current dot next is equal to previous. You can see 3 का next क्या है? 7. That is our previous. And 3 का next क्या है? यहाँ पर 8. So that will be our previous. If our previous is somehow here, it means definitely we are going up. If somehow our current is at this place and our previous at this place, it means we are traversing on upside, not on the downside. That's what the condition is. Current dot left is equal to previous and current dot right is equal to previous. It means definitely we are going upside. Understood, Vishal? Yeah. If any of the scenario you got previous and current in these positions, you can easily understand that you are going downside or you're going upside. Okay, I think that's what the important thing. Now we can jump into the code and logic part. Okay, that's what the code. So let's start, guys. Let's start our code. So we'll take one stack here. Yeah, so I will erase this part and I will take the stack here. So we'll use the same space. Yeah. Okay, so now our current node is 1 and current node we have pushed in the stack. Okay, so guys, whatever will be on our stack, whatever top element is in stack, that will be our current item. So now this time just remember it, whatever is in the stack, that will be our current item. Okay, so now you will see that current is this and null is this. So now current dot left, because you know that left, right and root. So right now our current is at this place and previous at null. Previous it is pointing out to null. This is the scenario. Are we good? Are we good with this? The first step? Are we good, guys, with the first step? Yeah, let's move further. Now let's go for the next element. And now let's move this current to here and move our previous to this place. Correct? Now we are going downside. Now we are going downside. Correct? Now we are going downside. So whenever we are going downside, we just need to go for the leaf element. Leaf element. Whenever we are going downside, just go for the left or leaf element. Where leaf element is where the left is pointing out to null or right is also pointing out to null. So simply continue your loop. So 1 is there. Now push 3 also here. C is here. Now P will be here. Now P will be here. Correct? And our current will be, first current was 3. Now current has become 7. Now 7 will be pushed here. Correct? So now we have reached. Now our current will, now we have reached to the we have reached to the last element where there is no left, there is no right. Correct, guys? We have reached to the leaf element where there is no left element, and there is no right element. So what we'll do? We'll simply print it, because see, our condition is what? Left, right, and root. We do not have any left, we do not have any right. So what we have now? Only the root. So that would be our answer. Let's put in an answer. Oh, we are not updating the previous also. So in previous, I think 1 and 3. Yeah, in previous 1, 3. Correct. And in answer, we have popped it out. We have popped it out the 7 and keep it here. Right, guys? Are we good? Are we good now? Yeah. And now, earlier, we were making our current item to the previous. But now, this time, our previous will be this. And current item, current node will always be stack top, which would be 3. Which would be 3. Understood this thing? This time, whenever we will pop it, we will just simply increase our previous one. And current item will be always be the stack top element. So now, after popping out, the current top has become C. Current top has become 3. Okay, so now let's jump into the code, guys. I will show you this part only in the code also. You can see this is my stack. This is list for keeping our answer. In this time we will push our answer in list. You can see the first root element I am pushing in stack. That would be 1. That would be 1. This element. Okay. And then my previous is null. You can see previous is null. Now when the stack dot length is not 0, we'll continuously traverse it. You can see I am taking my current item always in the next iteration, always from the stack top. This is a stack top. So first current will be 1, then current would be 3, then current would be 7. Always I am taking it from the current top item. Now this is the condition where we are going to look for the leaf node. You can see, go down the tree in search of a leaf node. So you can see, just ignore, if you do not want to ignore these conditions, you already understood. Whenever we are going downside or our previous is null. See, previous will be null only in the first scenario, first condition, this condition only. First time previous will be null. This previous will never be null after that otherwise. But you know these conditions. Whenever we are going downside, when previous dot left is equal to current or previous dot right is equal to current, if we do not have any left, if we do not have any right, simply pop it out. You can see, if I have any left, push into the stack. If I have any right side, push into the stack. But if I do not have any left, if I do not have any right, simply pop the top item from stack and push it into my answer. That's what we did also, guys. First we have all the 7 here, and once we see that there is no left, there is no right, what we did, we popped it out and push it into our answer 7. Correct? And you can see at the end of all these 3 conditions, you can see I am making always my previous as current. So now C will be the current, right? Before popping out, this was the scenario, right? Before popping out, this was the current, this was the previous. After this only we get to know that There is no left, there is no right. Correct, guys? Let me know in the chat. After this only, when we were at the 7, after that only we get to know that there is no left, there is no right. Once there is no left, there is no right, we will simply pop it. Simply pop it, this element. So we popped it out, this element, and put it into our answer. And then we make this popped item as our previous. So this previous will be gone from here, and this previous will be here. Then in next iteration, we'll again take the top element as our current item. So current will be here. Are we good now, guys? I will stop it here because this is the same thing is going to happen in each tree, each subtree. This is going to happen every time we are going to reach to the left leaf node, then print it out. After reaching the left leaf node, we are going to pop it from the stack, and then we are going to make this as our previous element. Everyone understood? Now what we need to go, now what we need to do, guys, we have already traversed to the left side, correct? And we are right now at the root element. We are right now at the root element. You can see we are right now at the root element. So now from the root element, what are the scenarios? Previous is equal to current alone. Once again, so previous is equal to current. See, every time we are making our previous, because see, there is nothing after this, right? So this will be our previous, right? There is nothing after that. So see, Hariharan, what we are doing, when we are at the 7, we find it out there is no left, there is no right. It means this is the, we have already traversed everything on the left side. So we need to push it, because our condition is left, right, and root. When we do not have left, when we do not have right, it means that this is the root. We need to print it. So what we did, from our stack, we have popped it out and push it into our answer. You can see, push it into our answer. And then we make our previous to this popped item. Because why we are doing that? Because now we need to go up. Because now we need to go up. Or why we need to go up? Because we need to traverse the right side as well. So that's why we did the previous is equal to current. So we can understand, our code can understand, now we are going up. Because we need to tell to our code that this is the up scenario, this is the down scenario. So we need to tell that. So that's why we updated the previous this, and now the top element will be our current. So now what we need to do, guys, we have to go up. So now you can see we are already up. We are already, 3 is our up element, 3 is the root element, 7 is there. Now we need to go to the right side. Correct? Now we need to go to the right side. So now what we'll do, we'll check into our code if current dot next, because you can see that's what we are checking into our code. The next, if you will see, this is the downside. Now the next thing which we are doing, guys, you can see if current dot left is equal to previous, it means we are coming from the left side. It means we are coming from the left side. We are coming up from the left side. So it means we need to go to the right side. If there is any right. If there is any right. So that's what we have written in the code. If current dot right is not equal to null, push it into the stack. If current dot, or if there is no right, if there is no right, then simply pop that element and push it into our answer. Because you know that we are already traversed the or the left side, but if there is no right, then take the root element only. Because there is no root, because there is no root element, right? Yeah, there is no right element, and traverse it. But right now in our case, we have the right element. So we will, what we'll do, we'll push this 8 into our stack. We'll push this 8 as our stack. And that's what you can see we are doing it as dot push current dot right. Correct? And then we'll make our previous again to current. So now this previous will become this current. Correct? Now you can see we are going downside. Now in the next iteration, this will become our current. So this will be our current. Now we are going downside. In downside, what we need to go? We have to go to the left side. So now we'll simply go to the left side. We'll push 14. We'll push 5. Correct? And now in this scenario, current will be here and previous will be here. Correct, guys? Understood this thing? Two scenarios only. go to the left side, and then we need to go to the upside, to the root, and then if there is any right, go to the right side. And if there is no right, then simply pop that element from the stack, because that is our root. You know that, right? In the stack top, we will always get the root. In the stack top, we always get the root. But we are not popping it out every time. We are not popping out root every time. If there is any right, we are pushing that right. We are not popping out route every time. Are we good, guys? Everyone? Hariharan, Suraj, Parag, Arad, Joseph. Not getting any response from you guys. You guys are there or not? Yes. Okay. Okay. So now, guys, we are again here. We are at the same situation. Our current item left and right is again, both are null. So what we need to do? We have to again pop the top item. So this is 5. And then we need to make this as our previous item. This will become previous. Same step. This will become previous. And now we'll remove this 5 from here. Correct? Now we remove this 5 from here. And now our top element is 14. So this will become current. It means right now we have to go up. So now our second condition will run. This one. If current dot left is equal to previous. Now second condition will run. So again, current dot left is equal to previous. Yes. So now what we need to do? We have to check if this also has any right element. See guys, we are going from here. Whenever we are going from the left side, always we need to check for the right side. But we do not have any right side. We do not have any right side. So that's why we'll go into the else part and update the pop. Do the popping here. So now 14 will be removed from here. Now 14 will be removed from here. And now again, same thing. Once we remove anything, we make that as a previous element. This is again our previous. And it has removed from here. Now what is the next, guys? Now what we need to do next? Guys, tell me, this time, is it not interesting? No, no, no. Before we have to make our current element. You can see there is no current element, right? So first we have to make our current element as a top. Whatever is in the stack, make that as a current element. Right? So first we'll make our current element. So this will become our current element. So once we are at the current element, we will check, is it up or down? Is it up or down? After making current element, we need to check, is it up or down? If it is up, we need to check from, is it coming from left side or right side? It is coming from left side or right side. If it is coming from left side, go for right. If it is coming from left side, go to right. So that's what we'll do. So you can see it is coming from left side, this arrow. So it means we need to go for right. But in the right, we do not have anything. So it means we need to, if we do not have anything on the right side, we need to pop it. Yes. So we will pop the 8 from there. We'll pop the 8 from there. And then whatever element we have popped, we'll make that as a previous element. Correct? Now what we need to do again? You guys tell me what we need to do again now in the next iteration? Yes, make current as top. So what is our current element right now? Which is 3. So now this will be current. Again, what is happening? Again, we will compare. Are we going down or up? After updating our current, are we going down or up? Up. From which side? From which side we are going up? Are we going from left side or from the right side? You see it and tell me from which side we are going up? From the right or left? From the right. If we are going from the right, we directly pop it. We do not need to go for right in this time. If we are already going up from the right side, we do not need to look for the right side element. We directly pop it. So that's why we'll directly pop the 3 from here and push it into our answer. If we are coming from the right side, no need to do go for right because we already coming from the right side. So, and now this 3 will become our previous. Now you guys tell me what is the next step. Now again we need to find out the current element. Again we need to find out the current element. And for that current element is 1. Correct? So after finding out the current element, what we need to check? After finding out the current element, what we need to check? Are we coming from, are we going up or are we going down? Are we going up or are we going down? So we are going again up. Now you tell me from which side we are going up. From which side we are going up? You see it here. From which side we are going up? We are going from the left. So what we need to do this time? When we are going from the left side, when we are going from the left side, what we need to do? Go right. So we will go for the right side. Correct? So in our stack, we will push the 6 here. And we'll make 1 as our previous element. Correct? 1 as a previous element. Now, what we need to do again, guys? After updating the previous, what we need to do again? Tell me in the chat. After assigning the previous, what we need to do next? No, Vishal. Yes. After, see, Vishal, you are forgetting every time. After assigning the previous, you need to find the current also, right? Then only you can find it out. You have to go up or down. So yes, this is the current element. You will put the current here. So now you guys tell me what is we need to find it out next. After finding out the current, what is the next step? Are we going up or are we going down? No, Hariran, that's not the step. Are we going up or are we going down? That's you need to find it out. Yes, this time we are going down. So once we are going downside, yes. So now if we are going downside, we need to go for left. Correct? We need to go for extreme. We need to go for extreme left. Extreme left mean we need to find out that left leaf which does not have left and right. So that's what we need to do. But you can see directly we got the null here. Directly we got the null here. So we will not go into the left side, but we'll go to the right side. Correct? Yeah, we do not have anything on the left side. So we'll go for right side this time. Correct? So now we'll first insert the 9 here. First insert the 9 here. Now this previous will become, this will become previous. Guys, do not forget this time. What is the next step again? Do not forget this time. What is the next system? Yes, make 9 as current. That's what, make 9 as current. Again, you will see that we are going down. So we need to look for left side. We need to look for left side. Now this will become previous and this will become current. We'll push the 10 here. Now 10 will become, see, this was not difficult. Now 10 will become our current. Sorry, previous. 10 will, now, yeah, 9 will become previous and 10 will become current. Again, we need to go for the left side because you can see we are again going downside. We are again going downside. So we'll again go for the 11. And this will be our previous now. This will be our previous. Now you go. Now we got the leaf node here. Now we got the leaf node here. I think this will be the scenario. Previous will be here and current will be here. Yeah. Now we can see current node does not have any leaf node. So what we will do in this scenario, we also do the popping. So first we will do the 11 here. Remove it from here. And make our 11 as previous. Correct? Now what we need to do, guys? Understood, right? The leap scenario. Everyone understood the leap scenario? Yes. So now we'll make current as a 10. And now you can see we are going up. Now we are seeing that we are going up. So now from which side? Yes, check if we are coming from left or right. From which side we are coming? left side. We are coming from left side. So what we need to do? We need to check the right side. We are coming from the left side. So you can see in the code also. That's what we are doing, guys, every time. You can see current left is equal to previous. It means we are going up. And that is also from left side. So then we are again checking if current dot right is equal to null. If there is any right, push it in the stack. Otherwise, if there is no right, simply pop it out. And you can see second condition also. If current dot right is equal to previous, it means we are coming from the right side. If we are coming from the right side, then simply do the popping and push it into our answer. And this is the scenario, the first scenario where we are just going downside. Previous dot left is equal to current, previous dot right is equal to current. If there is a left, push it in the stack. If there is a right, push it in the stack. And if there is no left, there is no right, start popping from there. Start popping from there. Same code is working there, guys. So now, because we are coming from the left side and there is no right, so we'll simply do the popping. So this will be popping, 10 will be there. Then I think same goes for 9 also. 9 will be there. Correct? And then we are coming from the right side. So 6 will be popped out. And then again we are coming from the right side. So 1 will be popped out. That's all answer, guys. I know that was little bit complicated, but if you have understood the code or the logic, there was only two logics actually. One is when we are going up, when we are going down. When we are going down, we need to look for the leaf node. And once we got the leaf node, pop it from the stack. If you do not got the leaf node, push it. Left element, right element, push it directly everything there. Once we got the leaf node, pop it from there. And once we done the popping, then we start going up. And then in the up, we just find it out from which direction we are coming. If we are coming from the left side, also check the right side because the post order is left right route. And if we are coming from the right side, it means we have already traversed the left, we have already traversed the right. Now we are at the root element, simply pop it from the stack. I hope it was little difficult, but did you guys get little bit interesting? Like, did you see it was little bit interesting? Yeah, actually, dry run helps a lot. And whoever has not understood, please try it. Please try it one more time. When you have little bit time, just try it with the dry run. Code is not difficult. Code is very easy. And you know that we have used only one stack. There are multiple solutions where people are using 2 or 3 stacks or multiple ways to solve the post order iteration. But we have only used one stack, and with 2 pointers we have solved it. Okay, guys. Input is in the form of array or linked list. It will be form of nodes. So input will be in the form of like this. Guys, input will be in the form of like this. Let me show you somewhere. Yeah, like this. There will be one node, then left of it, right of it. You know that, right? It's an object only. So that's what. In the linked list, as I showed you, when Ankit has asked in one way how the left and right was working, similar is here. Left child, right child, left dot left. Understood, Parag? How it is coming, how input is coming to you? It's an object. Input is coming in object. Which method is generally asked in the interview, the iterative one or recursive? Recursive one. Recursive one they ask, but you know the iterative one is used in. Sometimes they ask iterative one also because it's a little bit complicated. But see till now what I like in the interviews, if somebody has asked me, I have only given the recursive one because the iterative one is little bit difficult for DFS. So I always goes with the recursive one. But if somebody is like externally asking the iterative one, then I think yes. And you know, a lot of problems are there in the lead code. Though in those questions, you have to go for the iterative one. Otherwise, sometimes like the time complexity is more for the recursion. You will see that timeout exceeded. So then in those scenario, the recursion one is not good. Okay, guys. So now let's move the last one also, which is the BFS. Yes, iterative ones definitely help in logical thinking. So, guys, the last one, the BFS, it's very easy actually. It's not difficult. The traverse one is very easy. Let me show you now. Can we, before moving into that, are we guys, can we move into the next question, or do you guys still have anywhere small question? Let me know. I can answer it quickly. Then we can jump into the next one. Are we good? Can we move into the next one? BFS traversal. Yes. Okay. So guys, let's look for the same example. There for DFS also. 1, 3, 6, 7, 8, 14, 5, 9, 10, and 11. Guys, it's very easy. We just need to traverse level wise this time. This is first level. Then we need to traverse these two. Then we need to traverse these two, these three. Then we need to traverse these two. Then we need to traverse these two. So see guys, if we take a small queue here, a queue here, correct, and start our first element in, if we put our top or root element in the stack, so this would be 1, correct, and this is our answer. So we'll put a loop, and then our loop will start it, and our loop will start till our queue is not empty, till our queue is not empty. So what we need to do guys, we need to simply take it out this element, like we need to shift it and keep it into our answer 1. Now this, I'm also like keeping like whatever element we have kept it here. So 1 we have kept it, that's out. And before taking it out, push it left and right element of it. Push the left and right element of 1, 3, comma 6. Correct? 3, comma 6. Now take again the first element from the queue, which is 3. Put it into your answer and delete it from here. 3 is here now. Correct? So after deleting the 3, take again the left and right of it. 7 and 8. Correct? Are we good guys till now? Are we good now? We are just taking first element in the queue, and then we are taking it out, shifting it, and then whatever the left and right it has, I'm just pushing it into there. Yeah, similar to that. Similar to that. Yeah. So just simply pushing the 7 and 8 left and right of it. Now, what is the top in the queue? What is the front in the queue? It's again 6. Push it into an answer. Take it out of it. So now push all the left and right of it. There is nothing in the left. Push the 9 here. Now you can again take the 7 here. There is nothing in the queue for 7. So we will not push anything. Now let's go for 8. Take it out of our queue. Whatever child 8 has, push it there. 14. Okay. Push the 14 here. Correct. Now take the 9 out. Take the 9 out. Take the child of 9, which is 10. Now take the 14 out. Take the child of 14, which is 5. Now take the 10 out. Take the child of 10, which is 11. And now take the 5. There is no child. Take the 11. And guys, this is a BFS. You can see we have traversed BFS very easily with the help of Q. Just take the top element from the queue and push the childs of that particular node. Yes, anyone finds difficulty here? I think this was very easy, right? For everyone, anyone has any doubt, quickly tell me. Anyone has any doubt here? Yes, definitely it's easier than those three. Joseph, Arad, if you are still in the call, Hariharan, Parag, Suraj. Suraj or Joseph, anyone? You guys are still in the call? Okay, I think they are not in the class. Ah, okay. You have to watch the recordings, yeah? Okay, guys, so now we have already done the BFAs. Now there are two questions from the previous class. There are two questions from the previous class on BFS only. So let me show you and then we will quickly solve them. Okay. You can see this is our first problem. Given a binary tree, your task is find the height of it. And you know, height is the number of nodes present in the longest path of tree. Guys, till now, we have calculated the height based on the number of edges. Based on the number of edges. And they are saying height is the number of nodes present in the longest path of the tree. You can see in this tree, the height they are trying to find it out, which is like you can take any traversing 136 or 245. So the answer would be 3 here because the longest path is this one 136. This is our longest path. And how many nodes are there? 3 nodes. So that's what they are saying. The height is the number of nodes present in the longest path of the tree. Okay, understood the question? Everyone, we need to find out the tree height of the tree, but height of a tree is number of nodes in the longest path. Okay, so let's quickly look into our same question here in the queue. Just look for the same question here, or let's take the simple one which they have given in the question only, which was one. What is the question? 2, 3, 4, 5, and 6. Okay, guys, we are going to solve this question with BFS only. With BFS only. Correct? So here, so first, let's push this element. This is 1. We have pushed it out here. Correct? So before that, I have not shown you the code, right? I have not showed you the code for the BFS, right? Let me first show you the code for BFS. Then we will look into this one. Yeah, you can see we have taken first Q here, then Q dot push, this dot root. Then we are shifting the top element, and if there is anything in the left, Q dot push. If there is anything in the right, Q dot push, node dot right. This was the BFS code. Very easily, we were traversing it. Correct? Anyone finds any difficulty to understand this code? Are we good here? Yeah, are we good here? Okay. Yeah. Now, guys, we are going to make some changes in the same code to get the height. So height, they are telling number of nodes. What they are telling for the height? They are telling it's a number of node. So if somebody is asking you at this label, what would be the height? At this label, what would be the height, guys, here? It would be 1, right? What would be the height at this label? It would be 2, right? You can see number of nodes 2, right? If somebody is saying what would be the height at this label, So for this element, you can see it would be 3. For all of these elements, height would be 3. Am I right, guys? So you can see, no, that's also correct. That's also correct, Hariharan. That's also correct. I will tell you, wait for that. Because we are trying to do it from another way, which is the BFS. That's why I'm not looking into that. But this will, yours one will work in with a recursive approach. For node 3 and for H2. Yes, for HS2. Yes. Now, guys, you can see if somehow, if in each label, if in somehow, if it at each label, we can just simply 1 minute. Yeah, like after traversing each label, if we can simply if we can simply take a variable height is equal to 0, and once we traverse this label, we can simply increase this to height 1. Correct? Once we traverse this label, once we traverse all these nodes or all the nodes at this label, and then we simply need to increase the height. Correct? So somehow, if we can get that where our level is ending, we can simply add one increment our height variable, and then after traversing everything, we will get the final height. Is it right or not? After traversing all the label, if we somehow, so we what we need to find out, we just need to find out how can we know that where our level is ending. How can we know where our level is ending? Correct? Yeah, we will discuss about that, Ekta. So, but first tell me, guys, if we somehow able to find out where our level is ending, can we get the answer for our question? Everyone? Yes? Okay. So see, guys, what we'll do, first time we'll push one into this, one into our stack, one into our queue. And at that time, we will take the size of whatever current element is here, we'll take the size of it. So right now you can say size is 1. Correct? Right now we'll say size is 1. So what we'll do, we'll simply run our loop for whatever size is there. And size minus minus. That's what we are going to do, guys. So see, first time size is 1. So what we will do? Q dot shift. So now Q dot shift, and same logic. If node dot left, Q dot push, node dot left. So now, and if node dot right, same Q dot push, node dot right. And we will do it for both elements. So now because size is 1 here, 1 minute, guys. So because size is 1 here, so we'll just traverse one time. We'll just traverse one time. And outside of this while loop, we will simply height plus plus. Height plus plus. Now you can see once we will put out one outside, we will be getting 2 and 3. Correct? What would be the size now? It would be 2. So this loop will only be completed when we have already traversed all the elements at that label. After that, after 2, 3 will be ending, we will be getting 4, 5, and 6. Then size will become 3. So can you guys understand? With the help of size, we are able to understand the total number of element in that label. Total number of element in that label. We need to decrement size. We need to decrement our size. I mean, that's what we are already doing it at the end. Correct? So this code will look like this. While a q dot length is greater than 0, this would be the first file, and then we will take the size out of it. Let size is equal to q dot length, and then this size will, based on this size, this while loop will run, and then outside of this while loop, inside the first while loop, will increment the height plus plus. Everyone got it? It was not difficult, right? With the help of size only, we were able to find out. Correct, guys? Are we good now? Anyone has any doubt? Let me know in the chat. Okay, so now we'll see with the recursion way, but that logic would be for counting out the edges, for counting out the edges. If we want to count out the edges, so according to that, this would be height 0, right? This would be height 1, and this would be height 2. If we are counting out the edges, that would be the tree height of this tree would be 2, right, guys? If we are counting out the nodes, height is different, but our logic was counting out the edges. Correct? That was the height we have talked about. But in that question specifically, they have talked about that the height of tree is the count of nodes. But in the real scenario, but we have already seen that as we have talked about the height, it was the edges. Correct? So that's what's totally right. The logic for this would be like some as we reach at this place, as we reach at this. So see, if we find it out the height of this one, so just find it out the height for left subtree and right subtree. Which one is bigger? Just add +1 on that. We will get the height. We will get the answer here. So see, the simple logic is, which was Hariharan was telling, max of height of root dot left, comma height of root dot right, or +1. Will it give answer or not? Whatever the maximum height is here, if both are equal, see both scenarios, height is 1. You can see height is 1 here also, 1 is here. So for this tree, height is 1. So 1 and +2. If we just add one more into that, we'll get the height of tree also. Correct or not? Make sense or not? For BFS approach, let me show you the code with the BFS approach. Same tree, symmetry, node as height. Yeah, this is the code they are using, by the way. Yeah, I think, yeah, a similar code, right? Node count is equal to q dot length. So while node count is greater than 0, so they are shifting it out. Yeah, in node count, instead of node count, I have taken the size there. And this is the first loop which they are running. Here I was checking for q dot length greater than 0, but here they are checking for, they have just put the 1 is equal to 1. Okay, understood, Ekta? Yeah. So guys, did you understood the second one also? This one, max of height dot root and max of left tree height or right tree height. Whoever is the max, just add +1 on that. We'll get the answer here for the max height. Okay. So see guys, when we will reach to the last element where root is equal to null, at that time we just need to return -1, because see, for this element height is 0, right? Height is 0. So if left will return -1, right will return -1. So max of -1 comma -1 will become -1 and +1, because this one we are doing, it will give us 0. So for this element, height would be 0. So your recursion will stop where? Your recursion will stop if root is equal to null, return -1, else else if root is not null, then always find out this thing, max height of root dot left comma height of root dot right plus 1. Correct, guys? This would be the code for finding out the height in recursive approach. Let me show you the code also. We have this code. You see, this is the code. If node is equal to this dot root, you see, if node is this dot root, if node is equal to null, return -1. Otherwise, go for height node dot left, height node dot right. And at the end, mat dot max left comma right plus 1. That's what I did also. Understood, guys? Anyone has any questions there? There is one more question here. In the zigzag one, I want you guys to try it on the binary tree. Before that, I will explain you some more problems from the binary tree. If somebody is telling you, okay guys, so this one try it, the zigzag manner. Otherwise, we will talk about it in the next class. But before that, let's talk about two more questions. So yeah, okay. So let me show you. Let me tell you guys. So for the output for the zigzag, so zigzag works like this. Let me show you. Zigzag looks like this. 1, 2, 3, 4, 5, 6, and 7. So zigzag is like this. This is zigzag, guys. So output would be 1, then 3 comma 2, like this we will traverse. And then from the left side, 4, 5, 6, and 7. You see, from this side. And then again, so first time right to left, then left to right. No, sorry, first time left to right, then right to left, again left to right, right to left. That's how we need to traverse it. Understood? Yeah, little similar to BFS, but you need to think about when to traverse left, when to traverse right, at which label we need to traverse left, and which label we need to traverse from the right side. Very easy. It's very easy, but you just need to understand at which label I need to traverse from left side, at which label we need to traverse from right side. Okay. Okay, guys. So second question which we have, if we have a tree like this only, for everyone, if we have a tree like this, and if somebody is saying find the element 7 with the recursion approach, can we do that or not? Find the element 7, can we do that with recursion? So we just need to traverse left and right, and wherever root becomes 7, wherever root dot value becomes 7, we will say that it exists, we will return true. Otherwise, simply simply go for left, go for right, root dot left, and then root dot right, and use the same some function like find. Here also find, and this is all written in the find. Correct, guys? And we will be passing key here. Correct, guys? That's how we will be finding out the key. Simple, right? That's what is here also. You can see if node is equal to null, return false. If node is equal to data, return true. And then left and right. And then left or right click anywhere if we find it. If we find it on left or if we find it on the right, anywhere we find it out, we'll simply return our answer. Okay? It will work only in the case of distinct node values. If we have duplicate, it will work in duplicate as well. Because we are at the end, we are traversing whole tree. We are traversing whole tree. We are not stopping anywhere. We are traversing whole tree. And once we got the true, every time it will be true. Yeah, key mean target element. We have written the first matching key. We are not returning anything, Ekta. We are just returning that element exists or not. Yes, we are returning when the value found. Okay. Okay, there were two more questions, very related. I will just quickly explain you the logic. I think one you have in the assignment as well. That was if there are two trees, if there are one tree, are they symmetric to each other or not? Are they symmetric to each other or not? Symmetric means the mirror image. Symmetric means, guys, the mirror image. So, right? So, in the mirror, when you see somebody, so when you see left side, it looks on the right side, and when you see the right side, it looks on the left side. That happened on the mirror, right? And that's what the similar thing you need to check in the tree also. Is the tree symmetric or not? You can see if we have something like this 1 and 2, if we want to see the mirror image of it, it will look like this. Am I correct or not? Whatever is on the left side, it will look into the right side. Yes, it is. So guys, if we want to find out that this tree is symmetric or not, so I think we just need to look for any of the nodes. In any of the nodes, left and right should be equal. Left and right should be equal. You can see for the same root, if left and right are equal, then we can say, yes, it's a symmetric. Are we correct or not? Are we agree or not? You guys agree or not? If for the same node, if left node and right node are similar, we can say it's a symmetric. You can see here for the two left node and for the same two, if the right node, if both are same, it means this is symmetric. Same you can see for the two right node and for this two, if the if the 5 is, is similar, it means this tree is symmetric. Correct? This tree is symmetric. So now guys, the logic is very simple here. And the logic is, oh, see guys, uh, logic is very simple actually. So logic is, like if we considering this as a T1, so we'll pass, like in the same recursion, we'll pass same root as two different trees, T1 and T2, same root, T1 and T2. So we'll check that T1 dot value is equal to T2 dot value and T1 dot left is equal to T2 dot right and T1 dot right is equal to T2 dot left. If all are coming true, then our tree will be symmetric. Then our tree will be symmetric. Correct? And where we will be stopping it? where we will be stopping it. So that condition would be if T1 is equal to null and T2 is equal to null. Because both are null, then simply return true. Because if both positions like this and this are reaching at the same place, it means they are at the same label. They are at the same label. Because you can see we are traversing T1 and T1 dot left, T2 at left, T2 dot right at the same label, right? So that's why this would be the first condition, and false would be if T1 is equal to null or any one of them is null. Any one of them become null, it means we need to return false. Because we are passing T1 and T2 together. If any one of them is becoming null, it means something is wrong here. If 5 is here, like 6 is here, and T1 will be here at the null, it means this is the wrong condition. This is not the symmetric scenario. That's why we will be returning false from here. Understood this condition, guys? T1 and T21. We have the code for that also. Is symmetry. You can see T1 is equal to null, T2 is equal to null, return true. Otherwise, T1 dot val, T2 dot val. And you can see T1 dot right, T2 dot left, T1 dot left, T2 dot right. That's what we are passing. And there is one more question similar to that. Is same tree? Is same tree? Like question is like this. Same, बिल्कुल same logic is there. 1, 2, 3, and 4, 5. This time they are not asking symmetric. They are asking it is same or not. Sorry, the right side of tree or left side tree of same or not. So just in the same logic, you do not need to check T1 dot left is equal to T2 dot right. You just need to check T1 dot left is equal to T2 dot left. These should match. Is same tree is similar to a symmetry, but in the is same tree, you need to modify your condition rather than checking left and right. This time you need to check left, left, right, right, and the value again. Value you have to again check. These are the question available in your uh, assignments. So that's why I'm just giving you a hint. So you guys can just try to solve it. Okay. And for zigzag also, I'm giving you hint. You just need to take one flag. You just need to take one flag, and after traversing each label, you just need to change that flag. For everyone, I'm just giving you hint for zigzag also. You need to take one flag, and after every traversal, you need to change that flag. So first time you will be traversing like one first time it's true. So you need to read element from the left side, like zeroth index, first index, two index, something like that. Or like just think about it. How will you solve this question? Okay, guys. So that's all from today's class. I try to I tried to complete, I think, most of the binaries questions and some of the assignment question from the previous and today's as well. So just practice it in the next class. Wherever you guys is stuck, we'll definitely talk about those queries again. Okay, because these are the queries. These are not difficult. They just need some of your time. You just pick any of the queries, just try to solve it. You will automatically get the answer. These are not difficult queries. Okay. So, okay, guys, so let's meet into our next class on Friday, where I'm hoping we will be talking about the binary search tree, and then we will be solving some of the problems as well. And please do the practice and also try to solve your assignment question. I hope today you got a little bit. We have seen some of the interesting questions, and at the end also, I think some questions were interesting. I think yes, this all codes are push already. It's in the master. It's in the master branch, guys. Let me see what are the changes I did. Yeah. Some of the change, like some of the places you can see, I have not provided the example. Let me push into the master directly. Okay, all of the code already in the master branch. So some of the some of the newly example of trees, I have not provided the proper examples there. For I've just written the code, but I have not provided the examples. So do not like look at the end only about the code. Okay, guys. So that's all from today. If you guys stuck anywhere, I'm already available in LinkedIn. You guys can ask your queries in that group. Okay, guys. Good night.